Okay, welcome back. Still topic 11, anthropometry, the study of human body dimensions and measuring them. And this is the last subtopic on this, on topic 11, statistical and heuristic anthropometric calculations. So get your stats books back out and review, but fortunately there's only two. I'm sure that all of us are very familiar here. Sorry, I just had statistics bad-mouthed in front of me. I said, hey, come on, this is an engineer's bread and butter here. So mean and standard deviation, I'm showing you these equations, but we obviously have tools that, Excel, et cetera, that can calculate things for us. But it's also good to know why we focus on these metrics for what we're going to study next, because we're basically talking about Gaussian distributions that are characterized by their mean and standard deviation. And so if you can assume that normal distribution and you have these two measures, you can fairly reliably describe certain percentages of the population based on the range of standard deviations around the mean that you handle in your design. All right, just like this, right? So assume I'm designing for the middle, not the largest or the smallest. What this shows, and this is, here's the I guess, greater precision here, 68.3% of the population is accommodated if you know exactly what the mean and the standard deviation is, and you go one standard deviation on either side, and you say, those are our two design thresholds. This is what you can count on as far as the percentage of the population. So this matters for when we say things like, I want to accommodate 95% of the population. Well, we can see mathematically, if we can assume these distributions, which we always can in this class at least, this is how we can, use that math. All right. So this is actually, I'll point you to this slide, for exams and things, you can use your notes. And so just come back to this. But I also have in Canvas under supplementary materials, there is an anthropometric handout. And there's a couple things I'm referencing here, including this table, which I just felt, they go well together. Let's just include them all in one package thing. So if you want to print things out, for example. But I wanted to point out, this is so I'm going to call this the K chart table. I just realized we have another K factors thing when we do the point source correction. So I hope that's not too confusing. In this case, K is representing the number of standard deviations. Or I'm sorry, that's not true. Yes, it is. The number of standard deviations. So if I go 1.96 standard deviations smaller and larger than the mean, what does that mean? I follow this chart. It accounts for 95% of the total population. Okay, so one way to use this chart might be to look at the rightmost column first, determine how much of the population you're hoping to accommodate. Is it the middle? Is it the largest, or is it the smallest? And then these are going to be the K values that you're going to use mathematically if you know your X bar, which is the mean, and your S, which is your standard deviation. Okay, so, and this chart is sort of like a universal law of how Gaussian distributions work. So it doesn't matter the dimension that we're talking about, doesn't matter, any anthropometric calculation we use can use this same table, because it's always just relating to some distribution's mean and standard deviation and that relationship in a normal distribution. All right. So yeah, 1.96 is a common one you're going to need to use for things like the middle 95%. But realize here, if I'm designing for the middle 95%, I'm using a different K value than if I'm designing for example, the largest 95%, right? So if I want to get to the doorway height that 95% of people can walk through, maybe I need the mean plus 1.65 times the standard deviation to determine what that 95th percentile is. Okay, so I've got an example here. Let's say, first of all, you have to have a data set that allows you to get a mean and a standard deviation. And what we do here is only as good as the validity of those calculations. So if you have, a skewed distribution. If it's not truly normal, you may want to factor that in here. But in any case, assume we have a normal distribution. We've got enough data, that it follows that Gaussian shape. And we can calculate mean and standard deviation, or it's otherwise given to us. So maybe the Army did, a major anthropometric analysis of infant feet. They didn't, but imagine they did something on the scale of what they did with soldiers for this example. Then you could reliably say, okay, well, theirs is based on 100,000 humans being measured. Pretty good chance to say that that's going to be a nice Gaussian curve. And then you can, if they have the mean and standard deviation, you can feel better and better about that when there are more and more data. All right, so assume that data set's out there, and you get told that a newborn infant boy's foot has a mean of 4 inches and a standard deviation of 0.5 inches. And so however you get those data, that's a different part of this problem. But now your challenge here is design a pair of socks / knit a pair of socks for your new nephew. And so let's say, your brother or your sister or what you're the in-law, right? So you're the, it's not your child. So one of your siblings has a child. And so you say, well, they're a fairly large person. So let's say that we're going to go with a 90th percentile as our design standard here, because maybe we're designing, it's a little more serious to make sure it's large enough rather than, you can be too large, but you can't be too small. So we want to accommodate, a 90th percentile foot, okay, for this population. So we've got the mean, we've got the standard deviation, we've got the percentage that we want to accommodate, the 90th percentile. Now, wait a minute, what do we got here? Why am I going, 90th percentile? Yeah, I'm sorry. I'm looking right here because I'm designing for the largest, I'm not designing for the middle. So I find in my table the 90th percentile in this column. It's all about determining what your K value is. In this case, it's 1.28. So I take my mean value plus the K factor multiplied by the standard deviation, and I get 4.64 inches. So if I knit that sock, I want to make sure it's 4.64 inches, and then I can be I can be certain based on my data that there's a 90%, what I should say is that sock will fit the 90th percentile human boy infant foot. So hopefully you've picked your design standard right, so it will fit that child. Okay. And all right, homework time. Now, I think I mentioned in the previous subtopic that we're going to have to go back in time and use the previous version of this military standard. So right now, 2022, the most recent version of this standard is Mil Standard 1472H. That has all the latest, what the Army, would recommend for different, design factors. But one of the things that they moved with that latest revision is the infamous, or I should say famous, very commonly used anthropometric tables. So I was looking for where those were. I couldn't find them. I'm traveling now. I said, fine, I've got the old version. It's the same table. It's just in a different place. So I just went ahead and posted in the supplementary material, the supporting material for topic 11. I put the previous version of the standard, and I will point you towards Appendix B, page 329, ring. You're going to need to do this for your homework, so you got to be familiar with it also for exams. And this is what you're going to use for the majority of your homework. Now, there's a couple things I want to point out. Okay, so I'm actually going to go to this here in a minute, but there are several. Let's do it. All right, here we go. So you're going to get your topic 11. You're going to go to right down here, Military Standard 1472G. Again, H is the latest one. H comes after G. I want you to use the old one because it includes Appendix B, which we still need to use here in this class. So going right all the way down to page 300, at least the, come on now, give it to me. Oh, hotel internet is going to slow us down here. Sorry, folks. I think this is right. All right, well, that thing's just verify. Yes, page 329. Okay. All right, come on, buddy. So after it loads in your hotel room, you should be able to see something that looks like this. And there are a number of these figures. And so you're going to want to look, there's several pages of these in several tables. There's figures, then tables, figures, then tables. There are different populations. You'll see I've got the seated body dimensions and general forces. There's also a specific seated body dimensions for, like, for example, Air Force forces or you know, Air Forces, but also, you know, so look through that, because it's interesting to note that, you know, they do have slightly different anthropometric dimensions based on the demographic of which military division. And I suspect some of that has to do with what is done. So I'll just, you know, I'll stereotype a little bit and say it's more important for people's body dimensions to be of a certain size for a jet cockpit as opposed to a, you know, a ground-based vehicle. Jet cockpits are a little more constrained. Maybe a submarine, you know, takes a certain body type and size. So that's a reason why there are, you know, different forces broken down there. All right, let's see what we got. Here we go. Okay, oops, yeah, that's right. I have to go in the PDF pages. All right, here we go, 329. Sorry, folks. Here we go, great. So here's where it starts, right? So Appendix B, I guess, you know, PDF page 329, actual page 349, PDF, whatever. But yep, so look at each of these dimensions and realize we've got, again, several of these. So I could look at standing dimensions. Those are going to be slightly different from seated dimensions. And then we even have detail as far as, you know, okay, seating again, breadths. Okay, those aren't included so far. If we keep going, we can get to things like hands and feet. You might get a final exam question that asks about hands and feet, so know where to find this, right? Okay, so now that you've seen this, you know where to find it, you know how extensive it is. I just want to point out two more things. Okay, so standing body dimensions, general forces. In general, look really closely at your homework. I'm probably going to ask you to do your calculations with the general forces data. So make sure you're on the right page and not accidentally, oh, here, Army air crew, right? Or our Air Force pilots, right? So for example, we do have slight differences here. Next thing I want to point out that you don't overlook is we've got 5th percentile, 95th percentile, male and female, male and female. Make sure you're in the right column and don't assume, for example, like, oh, these two numbers are right next to each other. That's the 5th and 95th percent. You have to, if I say design for the males, make sure you look at the 5th for males and you look at the 95th for males. Last point to make sure you don't overlook, in parentheses, we have our units in inches, but the standard is to give them in centimeters. Look very closely at which units are being asked for and make sure you're solving in those units, okay? So again, yep, the standard is centimeters. So if I ask for inches, you're gonna have to look at the one in the, this is not right. It's the opposite, isn't it? It must be the, wait a minute. Oh, wait, that's why. Pounds and kilograms. I was like, wait a minute. No, yeah. Okay, so this makes sense, right? So centimeters and inches. I didn't see that this was weight in kilograms, but yeah, so there you go. Okay. All right, now back to this slide. A couple other points to make sure you keep in mind. These are, again, fit young men and women, 18 to, you know, young 20s. That does not represent much more than the population of people around that age and of a certain level of physical activity. So there's this is a very valuable, very reliable data set for that population. So you need to be honest about how different your design population might be from this group if you're going to use this data set. Very commonly, this data set is used just because of how extensive it is and how, how many people went into this, but there is, again, that fundamental difference there. Last point here, this is highlighted. You can add and subtract multiple dimensions. There's at least one of those on the homework assignment. There will be at least one need to add dimensions together in the final exam. Count on it. And I want you to realize that the way you should do that is to calculate your given percentile for each dimension and then add those linkages together. So, for example, don't do, I'm going to add everything together for the 5th percentile and everything together for the 95th percentile, and then find the point in between. Instead, I need you to find the popliteal height, which is the ground to the backside of the knee, 27. Wait, oh, shoot. I hope that's right. Let's make sure. Popliteal, 27. Here we go. Yep, popliteal height. You see it right there. So I may ask you, for example, I'm going to design for a seat belt, right? And where is the waist? Where is the lap belt position relative to the ground? What you might need to do anthropometrically is determine floor to popliteal height. And then, I guess we don't have the dimension. I guess you'd probably use 25 in this, 26 in this case, floor to the top of the knee. But you may have to add multiple dimensions together. And I think I have to go to a different chart to find it. Oh yeah, 24, there it is. So if I added 27 plus 24, maybe I could say, hey, that's the waist, and that's the distance from the ground where you could put the waist belt, the seat belt, right? But two ways you might do that mathematically. I could see, and if I wanted to design for, let's say, the 90th percentile, I need to calculate what that is for the popliteal, and I need to know 90th percentile for this dimension, which is elbow rest height, I guess, and add those two together after I've individually done the stats. Okay, good. So here's what's coming. Gonna have, okay. And so, yes, so again, the K factor, how we did it with the children's foot, we did the 90th percentile there. Imagine I'm going to make a sock that incorporates the length of the foot plus the length of the ankle, up the shin. Do the 90th percentile for the foot and add that to the 90th percentile for the, for the shin. But when I have, okay, I guess I didn't make this explicit in the notes, but I do want to make sure that is explicit. If I have the 5th percentile and the 95th percentile for population, ring, 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 that's all I need to solve for the mean and the standard deviation. Okay, so think about how that could be the case. But again, remember, you've got your K factor chart. You know what the mean is probably, because you can take these two and assume a normal Gaussian distribution. So yes, it is just basically the mean of these two values. 5th percentile, 95th percentile are equidistant from the mean. So what is the average of those two values? That's your mean. Your standard deviation, well, I know the number of standard deviations that it takes to get from the mean value to the 95th percentile or from the mean value to the 5th percentile. I know that. And so if I also remember my K chart, and I'm going to X bar plus K of S, and I want to get to 95, well, looks like my K factor is 1.65. So if I know, let me just do this actually, let's do it live. I don't think I do it otherwise. Yeah, let's do it live. Let's say I wanted to know, let's just look at this chart. Let me get my drawing. Okay, come on. Give me the drawing thing. It's not doing it. Give it to me. There we go. Okay. I'm just going to make up an example on the spot. Let's say we want the 90th percentile. Ooh, that's going to mess with us, but we're going to do it. 90th percentile for this dimension right here, mid shoulder height. Okay. And let's just make it, just for this one, let's go with females. So I want to design for the 90th percentile female mid-shoulder height. So I got this value. And I'm gonna have to grab my phone for the math, but we're gonna do the average of those two values, which let me just see if I can, no, I can't do the math. Not on the spot. Okay, let's go. Let's just do it in Excel so that I don't have to mess with this. Yeah. All right, so let's go back to this example here. So we're just gonna pick one of these dimensions, and I'm going to go ahead and say again, we're going to go with dimension 19, the mid-shoulder height, and we're designing for females. Let's just say I want to know the 90th percentile female mid-shoulder height. So I need the 5th percentile female, I need the 95th percentile female, and let's say I want it to be solved in inches. Okay, so I've got 22.4 inches, 25.3 inches. All right, now I've already opened my Excel and I've pre-populated, right? So if 90th percentile is what we're going for here, then and we got our two values in inches. First thing I need to calculate, because this database isn't going to give you the means. You got to figure them out yourself. But this is a reliable way to do it. I'm just going to add these two together, divide by 2. It's exactly the midpoint between the 5th and the 95th. So 22.4 plus 25.3. Oops, I need to. Okay, yes, of course. Let's put them in parentheses. Divided by 2. 23.85 is our mean. Well, what's our standard deviation? How can we possibly know that? Again, it's because we're assuming this normal Gaussian distribution, and we know this relationship holds true right here, that if we are solving for, let's say, if we know the value of the 95th percentile, okay, so 95th percentile, we have it right there, 25.3, and if we look at this, here's our 95th percentile, which K value goes with it? It's 1.65. So we need to go 1.65 standard deviations from the mean value to get to the 95th percentile, or from the mean value to get to the 5th percentile. If I add it or subtract it, I am 1.65 times whatever our standard deviation is will give us that value. So the only unknown we have right now is standard deviation, right? So we basically, if we know our 95th K value equals 1.65. And again, I got that because I'm designing for the 90th percentile, not for the middle 90%, which is a different question. I'm looking right here, the 90th percentile, and I see, 95th percentile, because I know that value. 95th percentile, 1.65. All right, K is 1.65. Then I know my equation is 25.3 equals 23.85, the mean, plus the K factor, 1.65, times whatever our standard deviation is. So now I'm going to solve for, of course, my standard deviation. So let's go equals 25.3 minus 23.85 equals that. And then that divided by 1.65. There we go. That's our standard deviation. Okay. We'll put that guy right here. Oops. Sorry, I have to format cells. Get out of here. Okay, let's just go. Okay, copy. There we go. All right, good. Now, let me determine what the 90th percentile is. Now, we already know 95th is 25.3. 90th should be a little bit smaller than that, a little bit closer to the mean. But again, we're going to use this same equation and the same K chart. We just now need a different value of K because we're no longer talking about the 95th percentile. We're talking about the 90th percentile. So we go to the 90th percentile right there. What is this K value? It's 1.28. So now for our 90th, we have, oops, 90th, we have k equals 1.28. We use the exact same equation. We know what the mean is. We know what the k value is. We know what the standard deviation is. So equals, here's our answer, equals the mean, 23.85. Because I'm going to the 90th, I am plus, right, the k factor. If I was going to the 10th percentile, you know, I have the same k factor, I'm just subtracting. So I'm going plus 1.28 times my standard deviation, which is that guy. There it is. That's the 90th percentile mid-shoulder female height. Sorry, 90th percentile female mid-shoulder height, 24.97. Okay, so there you go. That we're going to do that over and over a couple times for your homework. That was me doing a dry run of it, but I hope you may have to be a little clever in a couple examples there. But it's basically you're going to go to this data set. You're going to make sure you're looking at the right table. You're going to make sure you're looking at the right dimensions, and you're going to, you know, I recommend using Excel or some other, you know, tool for the statistics. All right, continuing here. So a couple of notes to keep in mind. So again, we basically covered at least the main, there's another technique I'm going to talk about in a minute, but at least the main aspects of using the military standard 1472G. That's the main way I'm going to ask you to do those analyses. So again, realize, you know, many of these dimensions don't correlate very well with each other. So if you were to measure my thumb length, and if you determined that my thumb length was, you know, the 80th percentile, that doesn't mean that my head size is also 80th percentile, or my butt size is also 80th, right? So you need to consider that each human has different body dimensions. They're not a universal like multiplier, right? So, but if you describe all of the human thumbs, yeah, I might have an 80th percentile thumb, and I might have an 100th percentile or a 99th percentile cabeza, right? Big coconut. But you know, in general, I'm going to have different dimensions and different, you know, different. I'm going to be at different percentile values for different dimensions. There we go. The truly average person does not exist. If you find someone with the 50th percentile foot length, you cannot count on any other body dimension also being 50th percentile. Okay. Now, again, that statistical method, mean and standard deviation, probably the main way I want you to think about how you do these anthropometric analyses. But there are a couple other shortcuts. And again, these are really useful for things like I don't have the specific population data that I need. If I'm designing, for example, I have a really good friend who designs hospital beds for gastric bypass patients, which are a lot of times, you know, at the far end of body mass, you know, the far large side. And he can't use these standards. So actually, I'm going to post this paper as part of our supplementary material. He has a pretty great paper in Human Factors where he did an anthropometric data collection of that specific population and used that analysis in the design of his company's, healthcare beds, hospital beds. I'll post it. It's Wigerman et al. I'm going to post it. All right, so this is another method, though, and this would be the kind of thing you could use if you had not quite the best data, but you knew, let's say you had a population of people and you're going to design for, you know, a seat back size. And you don't want people to come in and get these invasive measurements of their spine length and all that. So you just say, all right, everybody here, just tell me your height. And most people know within an inch, you know, within a certain precision what their height is. And if you know in general, okay, our population can be described by this mean height, then there are appropriate, realizing that you're doing approximations, there are appropriate methods where you might use these sorts of multipliers. And so I think this goes with an article written by a scientist named Ruse Bazar. It's also in that anthropometric handout. But, you know, note here, this might be something I ask about where if I say, hey, you're designing for a male population and your male population is 6 feet tall. That's probably not a good average. Let's say 5'10" on average, 5'7", so I'm taller. Let's say 5'7" is average. And then I may say, well, what is the 95th percentile shoulder height or eye height? And you could then use these multipliers. These are just basically, ratio multipliers here. This is kind of how it breaks down. And so the dimensions kind of skew, or the multipliers kind of skew based on if you're above or below the mean, which kind of makes sense. So, make sure you're using the closest possible value. If I ask you to use this sort of an approximation, I'm going to expect you to use your engineering intuition. If I give a value that's like, tell me the 75th percentile or the 90th percentile, you're not going to have a multiplier for that. You may have to do some interpolation. That's what engineers, are empowered to do. Okay. And just a couple other more detailed, versions of these sorts of proportion heuristics. So again, this is a shortcut. This is like, I don't know exactly the thumb length of everybody in this population, but I've got 10,000 people who reported their heights, and maybe I can use one of these heuristic approaches to approximate, what that population's thumb length might look like. Yep, and other dimensions as well. Here's my thumb length. All right. One of the last points here is to realize that most of these data, in fact, everything I've shown you here today, assumes that you're being measured while somebody is standing as tall and straight as they can and against a wall and not moving. And that's just not representative of how humans basically interact in the real world. So we have this fundamental distinction between static and dynamic anthropometry. Most of the time, I want you to think about dynamic anthropometry. Unfortunately, that's a much harder thing to measure, right, or to get a data set for. So we can get people to sit still and get really precise measures. It's hard to say limbo, and I'm going to measure very precisely how tall you are, right? So yes, humans have an ability to, reach further, to stand taller if they're on their tiptoes, and they can kind of stretch and bend and do creative things to, to extend their reach, to extend their height. This is part of the whole, humans being dynamic. And so functional anthropometry, this is, another area of study. This considers ranges of motion. And then there are a couple of, like heuristic rules of thumb here, basically assume, do I have it here on the next page? Maybe not. Sorry. Yeah. 30%. There it is. Sorry. So, forward and lateral reach, you can say, yeah, if I'm sitting real still and super stretch, like being in a static position, I can actually add 30% if I'm allowed to twist and turn my body. Consider 20%, I'm sorry, 30% if I want to easily reach it versus super stretch, 20% if I can twist and turn. Heights based on me stand as straight and tall as I can versus if I'm walking, I lose about 3% of my height, as in terms of functional anthropometry. Yes, up to 5% of elbow height should be considered the nature of the work. So I'm sorry, up to 5%, of the height for that dimension may depend on, are you doing light work or precision work, let's say, which maybe I need my hands up here closer to my face and therefore my elbows up higher? Or am I doing exertion work, physical work, where I maybe need the work spot or the elbow rest to be lower because I need more room for my arms to be able to produce force? Okay. Now, we did an example of one body dimension that was, a scalar dimension, or sorry, a length dimension. But there are other human, body measures that also follow these similar statistical patterns. You saw in the 1472G that they reported the weights for the 5th and 95th percentile of men and women. And then also you can look at physical capabilities like strength, like, force output for a muscle system. And so they'll follow a similar sort of statistical pattern. If you have similarly mean and standard deviation, you can do similar sorts of calculations here. All right. Yeah, and strength and endurance are also measures that, human factors or ergonomists may measure and consider percentiles of a population. All right, final slide on the topic. Thanks for hanging in there. Just a few things to not forget if you take these tasks into the real world, which is ultimately the goal, the skill set. Very important to recognize who is the user population, describe them as best you can, and realize if you're using a data set, if you're collecting your own data, there are limitations in how you interpret each of those. Realize again that there's a certain percentage of a population you want to handle that's usually not 100% because that is usually prohibitively expensive. And so it's much easier to say, let's handle 95% of the population and let's invest special tasks to accommodate those extremes that are not necessarily within our normal operations. Those individually may be super expensive, but overall it's a cheaper sort of approach to let those extreme outliers, when they do show that, when they do become something that needs to be addressed, do those on an individual basis. Adjustment is a great way to handle that too. This seat size will fit 90-95% of human body types. The other 5%, 2.5 on either side, maybe can be accommodated by some adjustment of the hardware there. And last point, remember, almost everything we've talked about here is assuming humans in a static posture. Humans in the real world are not like that. And so to recognize that difference and apply corrections if they're warranted. Okay, thanks. That is this one. Look for a homework assignment to be posted. And thanks for tuning in. All right. Bye, everyone.